Recording is rolling. So it's Thursday, May 12th. Today's the big day. You guys got AP Physics 1 exam at 11:30 in the gym. So remember how it's working. Since you got your second period, next period is third period. So tell your teacher you have to go to lunch at 11 o'clock. You guys brought your own lunch. If anybody forgot, I got some bars right here. Oh, hey, you guys see this whole gray tray full of goodies? What have I got here? I got something here. I got some bars. I got some spare calculators. Now I took a whole box of rulers down there already. Then I got a couple around here. There's also a whole box of pencils going on right here. Box of pencils. So if you think you might need a spare pencil, do it. Anything on this desk, if you want to borrow it for today, well, go ahead and have the bar. If you want to use the bar, not that back. But okay. Okay. So, all right. Let me Google that real fast because last I heard is that for physics they don't care. I went to a conference sometime back, and let's see, AP Physics FRQ pencil or pen. Right, I'm pretty sure they don't care what you use. Although for other classes, like you have to use ink, but right. See, College Board. Check this out. All right, yeah, so Google searches confirm that you guys can use either pencil or pen. So that's what I'm seeing. That's what I've been told in the past. So at least that's true for physics. Now, your other classes, you have to check individually, but for physics, pencil or pen on the upper case is fine. Okay. All right, so first question lined up is about tension in an Atwood. All right, you guys want to run over tension in an Atwood? So this would be like a unit 2 type question, just navigate that. Okay. So here we go. You know what? I should do? I should solve this both in terms of variables and with numbers side by side. I think I did this back in the day. It's pretty good. So okay. So let's have a Atwood with a massless pulley at the top and a couple of blocks tied together by a massless string. Let's see, it starts off something like this. I'll call this guy mass B. Okay, and I'll call this guy mass A. And if I'm tagging some numbers to it, let's call this guy like 5 kilograms and call this guy 2. So let's go 3 kilograms. So 5 versus 3. Okay, let's split the page. Okay. And solve in terms of variables on one side and solve in terms of numbers on the other side, so you guys can see like a side by side. Right. That's okay. So you guys get with that setup. Okay. Now, before I get going, let's say big picture. You can sort of work your way around this. If these were the exact same mass, then wouldn't there be zero acceleration in the system? And wouldn't the free body diagram on each one be just its weight down and the tension up? And wouldn't the tension in that case be equal to the weight of either block? So like if it was 5 kilograms and 5 kilograms, this would weigh 50 newtons and 50 newtons, and the tension string would also be 50 newtons, right? Yeah. Right. And if it was 3 kilograms, 3 kilograms, then it should be 30 newtons and 30 newtons for every single force. So 3 versus 5 kilograms. I know the weight of the big guy is 50 newtons. The weight of the little guy is 30 newtons, and the tension has to be somewhere between those two numbers. So if I got a number like I don't know the answer, but if I got 38 or 42, okay, this was believable because it's between 30 and 50 newtons. Okay. So yeah, there's different ways to go about this. The way I do it, and I've shown you guys, I'll do it here too, is I solve for acceleration first and then tension. There's a way you can solve for tension first, but I've never done so. I'm not going to do something new today. So the acceleration of the system, isn't it net force on total mass? Right, Newton's second law of motion, which would be now net force. I'm thinking external forces. So I'm ignoring the tension now. I'm just saying, well, there's 2 gravity forces driving the system. So wouldn't that be like mass B has a weight, mass A has a weight, right? MBG, MAG. Right? The difference between those two would be the net force driving the system. Right? And then the total mass move would be MB plus MA. Right? Right now, in terms of numbers, that's going to go, the acceleration of the system is that'd be 50 newtons minus 30 newtons. So all acting on 5 + 3 kilograms. Okay, so in general, it turns out to be difference over sum of masses all times the gravity field of the planet. And the specific numbers looks like 20 newtons acting on 8 kilograms, 20 over 8. Okay. Yeah, 2.5. It's a newton per kilogram or meter per second squared. Okay. Now that's the acceleration system. Okay. Now I can go next step and figure out, okay, what is the tension in the string? So let's do free body diagram, because you guys are gonna have to draw some free body diagrams here in a couple hours, right? So I got 50 newtons down here. I got 30 newtons down here. Right, and try to draw those to scale, right? And in fact, if you're using a ruler, probably they should be using a straight edge if they can, right? Right. There's a box of about anyway. Guys, if you don't have a plastic straight edge or a ruler on the exam, can you just take a paper and fold it and then use that as improvised straight edge? You can just do that, right? Right. Oh,
I'll voice this out.
All right, so there's also a tension in the string that's somewhere between these two, right? So it's more than 30 newtons, but less than 50 newtons. I'll call that F sub T. And it's the same tension in the string, right? There's only one tension in one string, right? Right. So what is that tension? Well, what I'm gonna do is just hone in on one of these blocks, one of these free body diagrams. Let's say the big one, right? You could do either one. I'll take the big one, right? Big one. So I'm gonna go back to F equals ma, net force equals mass times acceleration, but for a specific block, okay? And that block looks like MBG down minus the tension force up that we're solving for gives mass of that specific block times its own acceleration, okay? Where the acceleration, remember, is this whole fun expression right here. It feeds in right there, right? And then in terms of numbers, this is going to go 50 newtons down minus the tension force up that we're solving for results in 5 kilograms accelerating overall down, I'm calling down the positive direction, right, for my setup here, at 2.5 meters per second squared, which is this number right there. Right? So here, I'll just finish off the math, the numbers. Add over the tension, subtract over the 50 newtons. Force tension equals what is, yeah, 12.5 newtons. Hold on a minute. Being silly here. 50 newtons minus 12.5 newtons. Okay, which is like 37.5 newtons. Hey, remember a few minutes ago I was saying this was like 38 newtons. I could probably delete that. Actually, it was extremely close to that. So there you go. See, that's like a middle force between these two weights, which will overall accelerate the small block up and allow the large block to accelerate downward at the same rate. Right? Yeah.
If they throw a problem like this on the FRQ, don't you have to derive the A equals MA minus MB over as
Oh, this right here.
yeah, you can derive that.
Yeah. You might have to derive this from scratch. You might have to do exactly this right here for an FRQ. Yep, you might do it.
And if you do that, you get full points for like an FRQ.
Yeah, I would start from start by jotting this down. This is probably worth a point itself. Just writing Newton's second law of motion is worth a point. Right? Then substituting in values would be a point, and then getting the correct answer would be a point. So that could be 1, 2, 3 points right there. Right? Yeah. So whatever framework you use to solve something, make sure you at least write down a step. Here, the framework is Newton's second law of motion. But if it's conservation of energy, start off with sum of energy initial equals sum of energy final or something, right? Because that could be like the starting point. And if you skip that step, then it's like, well, you might miss a bunch of points. Okay.
Okay. My question was for like also regarding like acceleration. Wouldn't you also like label on the average, say like one side was going positive 2.5 meters per second, the other side was going negative 2.5 meters per second?
Okay. Yeah. Okay. So that depends on direction. So I would say this would be this acceleration could be downward for the large block or upward for the small block. So they might actually ask the question, like for one block, sometimes it is, it's the 5 kilogram block, what is its acceleration? And then you would actually want to specify a downward, just to make for sure, because that might be something that they grade for. Yeah, because of course, acceleration is a vector quantity, direction matters.
And
And
say downward, like in the problem itself, right? It'd be like a downward.
yeah, if they specify it themselves, like what is the downward acceleration of blah, 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 then they took care of it for you. But yeah, if they don't, it's probably a good idea to specify downward.
Okay.
Direction. Yeah,
How much time do we have for the pilot FRQs?
yeah, it's 90 minutes, right? Okay, so you get so 2 sections. It's a multiple choice section and the FRQ section. You get 90 minutes apiece.
And that's 50 questions, multiple choice?
Probably 50 questions. I remember the very first exam was 50, then for a few years it went to 40 questions, and then last year it was 50 questions. So I'm thinking you guys are probably gonna get 50 questions. Yeah, and those last 5 questions, how many answers are gonna bubble? 2, yeah, so the first 45 bubble 1, but the last 5 you guys are gonna bubble 2, right? You have to get them both right to get credit. Okay. Right, you guys good there? All right, okay, let's go back to here's my. There we go. Right. So here's all your topics again. Right. Again, I got some questions here I can throw up on the screen and we can start solving them. But what other questions do you guys have? What other questions do you guys have? So I've got tension and Atwood question. All right. I'll tell you what, last couple days I covered pretty much everything I wanted to cover anyway. So here, I'll just start going through these questions. Oh yeah, go ahead. Impulse. Yeah, let's do impulse. Impulse, good call. Oh, guys, impulse would be looking at which topics that fall into. Yeah, momentum and collisions, right? So kind of collision, think an impulse. Right? So impulse. Okay, that's like delta P. That's to say like a change in momentum, right? So you could say mass times change in velocity. Right? I guess if they wanted to be really tricky, what they could do. Here, I'll give you sort of a counterexample that you probably won't see, but just thinking like if they want to be really, really tricky, they could give you like a conveyor belt where there's like mass being dropped onto the conveyor belt as it's rolling along, in which case there might be changing mass at a constant velocity. You could have that. You could have delta M times some constant V, but I don't know. I've never seen that, and I doubt they would ask that. But I'm just saying this is not strictly true. This is just how I've always seen it, right? But where does that come from? That comes from applying a force for some time interval, doesn't it? Right? So these time intervals, if we're talking about collisions, right? It's usually like a fraction of a second, right? A bat hits a ball, bam, it's like, like a few milliseconds or something. Right? Oh, by the way, to go from milliseconds to seconds, you divide by 1,000, right? Millis 1,000, right? Like here, take a look at this ruler. This little tiny tick, little tiny tick mark, that's 1 millimeter, right? Do you think you would need 1,000 of those to get a whole meter stick? Right? Right. But okay, but it doesn't have to necessarily be a tiny fraction of a second, but it usually is for a collision. But in general, here, let's look at a graph of this. Okay. What type of graph should you probably be looking for this type question? How about a force versus time, right? Okay. And this graph might look like anything, but the most common shape it takes is something kind of like this. Okay. Because usually there's like a starting contact point, right? And then say a bat pushing against a ball, right? After like a tiny fraction of a second, now pushing maximal against the ball. Now the ball is starting to rebound the other way. And at this point, the ball leaves the bat and flies off opposite direction. Okay. And this area would be impulse, delta P. Right? Oh, another graph you could see, and this would be for the rotational version of this. Could you guys see torque versus time? Right. Actually, we did an example of this yesterday, didn't we? Right. Suppose you have like a constant torque. Right. Now the area under this curve is angular impulse, right? Or I should say a change in angular impulse, like acquired angular impulse. Right. So that's like the rotational analog to what this is linear. Let's do some numbers. Let's say we got a bat and a ball. And boing, right? So give you guys some numbers. Let's say the mass of the ball is 0.145 kilograms. Ooh, that would be a baseball. Say, the initial velocity was, call it 20 meters per second thrown towards the plate. And the final velocity is, let's say it's like 30 meters per second, like rebounded. Oh, hold on. I can't say velocity if I do that. I would have to say speed, right? Right. So if I want to say velocity, I have to amend this a little bit by doing what? Yeah, right, have to change direction, right? Right, so they might say speed of this and a speed of this, and you have to know, let's change the direction. So somebody has to be a negative, right? Okay. So we got that. And let's say that the time interval of the collision was like 0.050 seconds, right? So I might ask like, well, what's the average net force, the average force? Okay, so you could like solve for that, right? Right, so go F delta T equals M delta V. Okay. Errors about my vector quantities. Right, so we're solving for this. And notice I said average force, right? And I'll show you guys why I said that too. So can you pop in some numbers? Call this guy 0.05 seconds. Call this guy 0.145 kilograms. Call this guy, guys, what would my delta V be? Can you guys do your calculation in your head? 50, 50 meters per second, because 30 minus negative 20, difference between positive 30 and negative 20, that is 50, isn't it? Okay. Right, so here, let's crunch some numbers and see what is the average net force. Okay, so 0.145 times 50 on 0.05, looking at 145 newtons, right, of force. Right, but what's the deal with the average? Well, because put this on a graph, force versus time interval. Okay. Now the time interval I got 0.050 seconds, should be in seconds, right? Force in newtons. Okay. What's probably gonna look like is that triangle type looking graph that I just showed you guys a moment ago. And think, how's this equation going to translate to this graph? If I have some kind of force times time interval, that's like the height of this graph times the base times height. Wouldn't that create like a rectangle shape? Rectangle shape, right? And that's supposed to represent the impulse, and I have a triangle, right? That's because we're talking about F average. Okay. That is, here's where 145 newtons goes, like right at this dash line. Okay. So guys, is the area of this rectangle and the area of this triangle the same?
Yeah.
Yeah. Right. So who can tell me just at a glance by looking at that graph, what is the maximum force on the space ball? Yeah, it's whatever 2 times that is, right? It's like a 290. You guys said 290. Yeah. So yeah, 290 newtons is all the way up here. This is 290 newtons up here. Ooh. Okay. So if this baseball, let's say like the seams would break anything above 200 newtons, right? So 200 newtons, so the seams break. Right? Is the baseball okay? Well, if you do this equation at a glance, oh, okay, it's under 200 newtons. But you say, oh, hold on, that's the average force, not the maximum force. So yeah, baseball does go apart. Ooh. Okay. Okay. You guys got it? What other questions do you guys have about this one? Sorry. Oh, yeah.
This may be a simple question, but how did you derive like the force times the change in time equals the mass times the change in velocity? How did you derive that?
See that is
On the equation?
Yeah.
Also, could you just use F equals MA?
yeah, actually this is really closely related to F equals ma. All right, so here's impulse on the equation sheet. So change momentum. No, change momentum, like the mass and change velocity, right? Force times time interval. So it's about a third of the way down the page. Yeah.
So we just
Yeah, and actually, no, you're right. I'm glad you mentioned, because this is really closely related to Newton's second law of motion. Let me show you guys the connection. So force times time interval equals mass times change in velocity. Right? Got 2 vectors, 2 scalars. Okay. But if I take the time interval and divide it down, wouldn't that be force is equal to mass times the rate change of velocity? Rate change of velocity, that's acceleration. F equals m a. Yeah, so there you go. Right there, right? Yeah, good call. Right. Right.
Will they?
How about this? Do you guys want to do the baseball bouncing off the paddle wheel?
Oh, no.
Here, oh, we'll cover it real fast.
That is like the scariest.
All right, so baseball, the boing, bounce off this paddle wheel. Let's have, give you guys, let's have the mass of the ball as 0.145 kilograms again. We'll have initial velocity be, here, I'll call it left negative, so here, let's do the same as before. No, I can't quite do that, because, right, it can't rebound faster. It could with the bat, because that's hitting it, but, so let's go negative 20 meters per second to V final being, let's say positive 12 meters per second. So boing, okay, gonna set the thing in motion, but how fast does this thing rotate? Okay, well, like what is the omega? Okay, well, you have to know something else. You have to know, oh, I should have said, you still have to know that the time interval of rebound. So let's call it like 0.10 seconds. Okay. You have to know the rotational inertia of the whole wheel. So now AP almost always gives you this, or they might tell you the formula that you could calculate some version of MR squared. Might be half MR squared if it's a solid disk, might be MR squared if it's closer to a ring, but they might just say it's like 45 kilogram meter squared, something like that. But MR squared, wouldn't that be kilogram per meter squared? Okay. This is rotational inertia. It takes the place of mass, but in a rotational context. So this is for the paddle wheel. So rotational inertia only counts for the paddle wheel. Right. Right. So how would you solve this? Okay. Well, this is an angular impulse question. So delta L. So change in momentum, but in an angular or rotational sense. Okay. So that could be, couldn't that be I times change in omega? Right. And if it starts from rest, then the final omega would just be the change in omega. Right. Okay. So I have I could just feed that in right there. This delta L. Well, okay. Now there's a formula I told you guys to have to memorize. So it's good we're covering this here. What is the angular momentum of a point mass? Yeah. It's regular momentum mv times the radial distance. Okay, that's what else I had to give you. I had to give you guys the radial size of this paddle wheel. Let's call it 1.7 meters. Just make up a number, right? MVR, right? So, yes. So the fact that this baseball is hitting at this radial size, right? Isn't this going to like cause a torque? Right. Now we're going to cut through torque. I'm not going to write torque on this page, but there is a torque involved. Right? We're going to cut straight to angular momentum though. This could be torque times time, right? So, actually, you know, here I don't think I had to give you guys the time interval for this, right? I think that's excess information. Although you could use this to go back and solve for torque. Okay. So we're doing an MVR for the baseball. So MVR the baseball results in I times change in omega of the disc. And if it starts from rest, then that would just be omega final, and we're going to solve for that. Okay. So here, just do the rest of my calculator because we've got mass here. It's 0.145 kilograms. We got the this should be a change of velocity of the ball, shouldn't it? For like, right? What number should I plug in for delta V? 32, right? I see 32. Good call. Good call. So times 32. Okay. Times the radial size of 1.7 meters. Okay. Then divide down the rotational inertia, 45 kilogram meters squared. Okay. And looks like my delta T was just excess information. You don't actually need to solve this problem. Okay. That is 0.175. And what would the unit be? Radians per second. Good call. Radians per second, because it's omega, right? How fast is it spinning? Of course, if it's frictionless, which is probably the assumption they would spell out for you. Okay. All right, looking good. It's a pretty tough one there, but you guys got that? I'll put smash down on the page. Right. What other questions you guys got right now? Okay, let's take a look at this list. Right, what are the questions? Okay. All right, so I'll pull some of these AP questions. Let's do this.